Welcome to the Phenomenological Alliance channel. In this video, we will discuss the next question that phenomenology poses in the field of natural sciences, namely, the problem of going beyond the framework of appearance.
The development of the idea that light is a kind of vibration, similar to how sound is a vibration of matter, has a long history. The Italian priest and naturalist Francesco Maria Grimaldi observed in 1665 that there are circumstances in which light can cancel each other out.
Through careful observations of the shadows cast by opaque bodies, we found that the shadow boundary between light and dark is not sharply defined. A series of colored streaks or fringes appear just outside and parallel to the shadow region. When observing the shadow of a thin rod, the colored fringes inside the shadow can be identified.
Afterward, Huygens proposed the theory of the wave nature of light, but rigorous experimental confirmation of the theory was awaited. These confirmations came through the Young and Fresnel experiments. Thomas Young's experiment from 1801 can be expressed as follows.
The light ray that passes through the double slit deviates from the rectilinear path and forms fringes on the screen.
Young attributed these phenomena to the wave properties of light.
The wave nature of light causes the light waves passing through the two slits to interfere, producing bright and dark bands on the screen, a result that would not be expected if light consisted of classical particles.
The theory of the wave nature of light was mathematically confirmed through the works of Augustin John Fresnel.
A Fresnel biprism consists of two thin prisms joined at their bases to form an isosceles triangle. In the region of superposition, interference occurs because two virtual sources of light exist.
Another experiment that demonstrates interference involves reflecting light from two black mirrors with a very small but adjustable angle between the normals to the mirror planes. The superposition of the light waves produces interference, which can be observed using a magnifying glass.
Instead of sketches that model perception, let's become aware of what we really see in the given experiments. Here we have two black mirrors, which are glass panels made of black glass. Placing these mirrors opposite each other multiplies the figures. Instead of one candle, we see many candles. Now let's shift our focus from the image of a candle to the image of rectangular light source. It is a rectangular opening covered with the green filter. Basically, we are looking at the image of a green square on a black background. When this image is projected onto the screen, we see a green square on a black background. If this image is multiplied by means of opposite mirrors and projected onto the screen, we observe interfering stripes. Instead of one green square, we observe multiple instances of it. In all interference experiments, figures multiply. In Fresnel's biprism experiment, this multiplication is illustrated through two virtual light sources. When observing a green square on a black background through the biprism, the image of the green square on the black background multiplies and overlaps. The simultaneous perception of several images causes the merging of impressions into one impression. When the image is viewed through the aperture, the image can be sharpened. The image before us displays the circular light source, practically the image of the white circle on a black background. After focusing, we see the original image on the screen. Noteworthy, the whole image with its bright and dark parts. When the image is viewed through two closed apertures, the figure overlaps. When the monochromatic light source is viewed through diffraction glasses, which have many small apertures, it's clearly visible that the image is multiplied. These experiments do not prove that light can cancel each other out. The real phenomenon is not the light tunneling, but the image multiplication.
Phenomenology focuses on the structure of conscious experience, exploring a scientific methodology capable of investigating it. Modern science uses a methodology that consists of the following steps: formulation of questions, setting up the hypothesis, defining a mathematical model, designing the experiment, analyzing the results by confirming expectations. The phenomenological approach highlights the limitations of such a methodology. Every hypothesis is based on a range of initial convictions which, as a rule, are never considered in the context of a theory. Focusing on the narrow scope of the observed phenomena to prove the initial assumptions raises doubt that we have covered all possible phenomena in all their breadth and diversity. The experiments are designed to confirm precisely those convictions that one tries to prove by the hypothesis. We can never know whether a newly spotted phenomenon is going to completely refute the initial hypothesis. Hypotheses and theories can only be refuted, but never proven with certainty.
From this example, we see how incorrect ideas can receive scientific confirmation. The belief in the counterintuitive idea that light cancels each other out is validated by experiments that support the initial conviction. Subsequently, through experimental suggestiveness and the exclusion of human perception, this idea becomes part of public opinion. Instead of the concept of light waves, the phenomenological approach investigates why the perception of the image is deformed when the image is viewed through small openings. Light waves are outside the framework of appearance. Interestingly, the idea of light waves' existence did not harm the technical development in optics, because the phenomena manifest themselves independently of our interpretations. Nevertheless, these experiments had a devastating impact on the understanding of the universe.